Hi everyone. Feedback from today. Let's see. What exactly is pKa? Essentially, it's just Ka. It's just the equilibrium constant. It's a mathematical shorthand for the equilibrium constant. It's defined the same way pH is. pH is a measure of the hydronium concentration in acids and base solutions. This can vary by many orders of magnitude, anywhere from 10 to the negative 10 to 10 to the negative 14. Very, very, very large ranges in terms of their order of magnitude, and we frequently just care about what is that order of magnitude, and that's what we use for the pH for. Same thing for pKa. pKa is defined the exact same way because the equilibrium constants for acid dissociation and base dissociation can vary by many orders of magnitude. So if, for instance, you have a Ka of around 10 to the negative 5, your pKa should be equal to 5. If your Ka is 10 to the negative 1, then you have a pKa of 1. And so generally acids that have lower values of pKa's have higher values of Ka's. They go more to completion than other acids, and so we say you have a lower pKa, you have a stronger acid. How do you determine the conjugate bases in acids? Is it only for weak acids? It's technically not only for weak acids. There is such thing as the conjugate base of a strong acid, and there is such thing as the conjugate acid of a strong base. But we normally don't worry about those in terms of their acidic or basic character. So how do you determine what the conjugate base or conjugate acid is? Well, let's think of it. Let's say I have a weak acid. I'll say HCN, hydrogen cyanide, cyanic acid, which is a weak acid. What is its conjugate base? So its conjugate base is whatever it becomes after it has lost its proton, after it's donated its proton, acted as a base, acted as an acid, donated its proton. So after it loses its proton, so it loses a hydrogen and a positive charge, so it should have a net negative charge, just to make sure we have conservation of charge. So this should be its conjugate base after it has lost its proton. And the same way for bases, if I have some base like NH3, and I want to know, okay, what is its conjugate acid? It's a base, so it is a proton donor. So you add on a hydrogen, a proton ion. So it should be NH4+. And your question was, is this only for weak acids and weak bases? No, you can talk about the conjugate base of a strong acid like HCl. The conjugate base of a strong acid like HCl is the chloride ion. We don't normally think of it like a base because its basic character is very, very poor. So you can talk about the Kb, its tendency to behave as a base. And there is a relationship between the basic character of a conjugate base and the acidic character of something's conjugate acid. So if I have, so point being here, let's say I can write a Ka. I can write a Ka for HCl, for this reaction, and I can also ascribe a Kb for Cl- for HCl's conjugate base. And I can generally say that the product of an acid's acid dissociation constant and its conjugate base's base dissociation constant, their product should be related to the autoionization constant. Point being that these two are inversely proportional to each other. The stronger the acid, the weaker its conjugate base. So we normally don't worry about the basic properties of the conjugate base of a strong acid, because as a strong acid, it is a very, very strong acid. It has a very large Ka, which means the Kb, the basic character of its conjugate base, is very, very weak, and so we usually don't even worry about it. We will usually only concern ourselves with the basic character of the conjugate base of a weak acid, and we will concern ourselves with the acidic character of the conjugate acid of a weak base, like ammonia. We usually won't care about the conjugate base of strong acids. Does the half equivalence point always determine pKa? So this was about today's discussion about titrations, where I made this assertion that if you look at the pH curve of the titration of a titration of a weak acid with a strong base. And your question was, does the half equivalence point always determine the Ka? Because I asserted that the pH at the half equivalence point should be equal to the pKa of the weak acid being titrated. It is not always equal to. It is always equal to it if you are titrating a weak acid. If you're titrating a strong acid with a strong base, the half equivalence point has nothing to do with the Ka of that strong acid. So it's only going to be true for weak acids, and I'll emphasize, only true for weak acids. You can have the titration of a weak base with a strong acid, like your analyte could be HCl. Sorry, your analyte might be a weak base like ammonia, and then your titrant, which you're slowly adding, could be hydrochloric acid. And then you could do a similar analysis. And that one's going to basically look like the inverse of this. You will still have initially a pH drop, and then it will level out in the buffering region, and then it will drop again once you pass the equivalence point. So you would have the equivalence here. The half equivalence point, you can show here that in this case, the half equivalence point, the pH should actually be equal to the P. Oh, am I going to get this wrong? Ooh, I'm just recognizing I might have that wrong. But I'm pretty certain. You know what? I'm not going to make that statement because I haven't checked that derivation yet. So I was going to say that it will be equal to the pKb of the weak base, but I just realized I'm not 100% certain about that. So let me double check that, and I'll make that assertion later to people. But the short answer is to answer your original question. The pH will be equal to the pKa, but only if you're at the half equivalence point, but only if you're titrating a weak acid. For a weak base, I think actually the POH, what I will say is that the POH, I'm pretty sure this is correct, the POH will be equal to the pKb of your weak acid. Of your weak base. So yeah, so there's that. How do you calculate pKa if the pH is given? So you're saying, how do I get pKa given pH? So again, it kind of depends on a case-by-case basis, but generally speaking, if you have a pKa, you're talking about a weak acid. Ka, we already asserted, is just a measure of the acid dissociation constant. The pH is just a measure of hydronium concentration. Those two are related to each other by the law of mass action for the acid dissociation. So to calculate Ka or to calculate pKa given the pH or the hydronium concentration, you also need to know these concentrations. So if you were dealing with a buffer, you'd need to know, okay, what's the proportion of conjugate base to weak acid? If you were dealing with just a pure acid, you'd want to know, okay, what's the concentration of the weak acid? And you can assume that the weak base concentration, conjugate base concentrations equal to the hydronium concentration. If you have just a weak acid, you can make that approximate, or you can make that assumption. But the point being, your question was, how do you calculate it? You would need to know these values. So the problem would either tell you what those values were, or you would have to infer their value based upon other information given in the problem. How do you calculate pKa with pH given? Again, if you're doing it at the half equivalence point, if you're doing like a buffer solution or you're doing a titration of a weak acid with a strong base, you create a buffer solution and then you can say pH is equal to pKa. But that's on a very specific case. At the equivalence volume of a weak acid titration with a strong base, so one like this, you said it behaves like a base, but does that mean it is basic or just slightly basic? You know, I would say I don't make any distinction between saying something is basic versus something is slightly basic. I would say that at the V equivalence, I would say, so this is going to, it would be basic, meaning that the pH would be, it's supposed to be a greater than symbol, greater than 7. So it's not going to be very much more than 7, but it will be more than 7. So I guess if I had to describe it, I would say that it is slightly basic. Slightly basic in the sense that what causes it to be basic is the conjugate base of this weak acid. But because it's a weak acid, its conjugate base is a base, but it's not as strong of a base as the weak acid is an acid. So short answer is it will be slightly basic. But I think it's trying to make a distinction between whether something is basic or slightly basic is a bit of an argument in semantics. So I guess if I had to choose one, I would say slightly basic. Because you are dealing with a very weak base, but a weak base nonetheless. Why is it that you have, so this is reiterating something we discussed about, could you please explain why do the different titrations for weak acid, strong acid, why do they have different shapes, curves? Why is the pH at the equivalence point basic? And so I'll answer both of those again. So let me put this up here. If I have the titration of a strong acid with a strong base, its pH curve is going to look something like that. A weak acid, its pH curve is going to look more like that. So we'll have like this little inflection point here. Why do they have different curves? Is because the actual equilibria are different between these two chemical systems. That's a fundamental difference between reacting a strong acid versus neutralizing a strong acid versus neutralizing a weak acid. When you neutralize a strong acid, all you get are water and neutral ions. So like, for example, the example here, we had sodium hydroxide reacting with HCl. We get sodium plus, chloride minus, and water. Chlorine is the conjugate base of a strong acid, and sodium is the conjugate acid of a strong base, meaning that neither of them is very acidic or basic. When you are titrating a weak acid, you convert some of you convert some of that weak acid, so I might say something like hydrofluoric acid with sodium hydroxide. That reaction goes to completion and gives you sodium ions, fluoride ions, and water. But the fluoride ion is the conjugate base of a weak acid. So it has a tendency to take back protons and become HF. So you basically, when you're titrating a weak acid, you will have an acidic component present, and you will also have a basic component present, where the basic component is the product of this neutralization reaction. You don't just go get sodium and you don't just get two spectator ions. One of those ions has the capability of behaving like a base. And so that gives you a decidedly different pH curve. The simple fact that you have now a conjugate base to a weak acid, you have a buffer region here. So the pH of the buffer is going to be somewhat resistant to pH changes. Why is the pH at the equivalence point slightly basic? Again, it's slightly basic because at the equivalence point, you have converted all of your acid into its conjugate base. And that conjugate base can behave like a base and make the solution slightly basic. So the fluoride ion reacts with water as a base and produces hydrofluoric acid and hydroxide ions. And the presence of those hydroxide ions causes the solution to be slightly basic. So you had a second question here, which was very interesting. Why are the curves different lengths? Meaning, why is it so? This is not going to be as clear here, but you were basically saying the height of this curve for the weak acid was shorter than the height of curve for the strong acid. Partly. So here's the thing: they should have the same height. Meaning like the final pH should be the same, because again, once you go past the equivalence point, the pH up here is due to the addition of base, meaning addition of the strong base. The idea is that you are adding sodium hydroxide. You've neutralized this solution, and now you're just adding on a bunch more sodium hydroxide. If you were using 1 molar, I'm going to make up some numbers here. Let's say you were using 1 molar NaOH, and you had, again, I'm going to make up a few numbers here, and you had 1 milliliter of HCl, and let's say you added, I don't know, 3 liters of sodium hydroxide. So if you added 3 liters of sodium hydroxide, only 1 milliliter of it is going to be used to neutralize the HCl, and then the rest is basically you're just diluting down your sodium hydroxide. You're just transferring sodium hydroxide from the burette into the flask. The reaction is done. You're just transferring it. So the pH at that point should just be dependent upon whatever the pH of your sodium hydroxide solution was. So the point being that they should rise to the same value. The curve is slightly different here simply because you create this buffer region. So the idea is normally this curve would look something like this, where it's like, okay, there's this smooth increase. There's this slow but consistent increase in pH that you would get for a strong acid. But you don't have that with the buffer. With the buffer, you get this immediate rise in the pH and when you create the buffer, and then it's flat. So it's the fact that there's this buffer region here which has a high but constant pH. So you already rise up a little bit, and then you rise to the same point later on. This one you're starting low and then you rise. Here you start a little bit higher because again it's a weak acid. If you're assuming that you're starting with the same concentrations between the two of them, this one's going to start with a slightly higher pH, and so it won't have to rise as much to get to the pH of your titrant after you've added excess base. So it's an interesting question. Not one I would ever. I don't know how I could construct a question about that for an exam, but it's an interesting question. So I hope I've answered that to your to your satisfaction. I've never been asked that question before, so I hope that's okay. How do you tell? Let's see. How do you tell pKa and Ka from looking at the graph? Again, you look at the half equivalence point if you're dealing with a weak acid. The half equivalence point, the pH at that point should be equal to the pKa. Second question, how do you find the half equivalence point? So you figure out whatever the equivalence volume is. So if you're looking at the graph, it should be fairly obvious. It's wherever you see the sharp rise in the pH, and basically the midpoint of that rise, that is the equivalence volume. The half equivalence volume is just half of that. So you guys will do that in your lab this week. You're going to do the lab this week, and then you're going to do the analysis in the week after spring break. You will figure out the equivalence volume by looking at it graphically. The half equivalence volume is just half of that. So you figure out half the equivalence volume by first figuring out the equivalence volume. Okay, so this is one of the questions I asked. Why did B, I had these two charts for these two weak acids. Why did B have a higher Ka value? So let me recreate these. So they were two charts, or rather two titration curves for weak acids. One of them was A, and it looked like this. B looked like this. So for people who are in my 9 a.m. class, I changed the wording of this question a little bit. The way I first asked it, I asked which one has a higher Ka value. These are two different weak acids. So again, between these two, you can say, okay, the pH at the half equivalence point, that looks like about the half equivalence point to me. So the pH over here was quite high. Over here, again, the pH at the half equivalence point, that's going to be right around here. This one has a lower pH, so I can say, okay, at the equivalence point, the pH should be equal to the pKa. So between A and B, I can say that A has a higher pKa. B, on the other hand, has a higher Ka, because we defined pKa as the negative log of Ka. So if your Ka value, or rather if your pKa value, and again, I already did this, but I'll do it again. If your pKa is equal to 5, then your Ka is equal to 10 to the negative 5. And if your pKa were 1, then your Ka would be 10 to the negative 1. They're essentially inversely proportional. The higher the Ka value, the lower the pKa value. In the same way that the more acidic a solution is, the higher its hydronium concentration, the lower its pH. So they're inversely related to each other. So if your instinct was to say that this one should have a higher value, you're right that it has a higher value of pKa, and that's mostly what I wanted people to see. I thought I would make it a little bit trickier by asking people to make a relationship between notice the relationship, the inverse relationship between Ka and pKa. For the 9 a.m. class, I figured that was unnecessarily tricky, so I made a change between them. On the titration curves of the two acids, can't you, okay, so this is another question somebody asked. On the titration curves of two weak acids, couldn't you just determine Ka based on the initial acidity of hydronium? So in theory, yeah, you could say, okay, the Ka should be equal to the hydronium concentration times the concentration of the weak acid's conjugate base over the concentration of that weak acid. And if you can measure the pH, you know that the pH should be equal to negative log of the hydronium concentration. You can measure pH, then you know the hydronium concentration. Can't you just predict Ka from that? You can, but only if you know these concentrations. You need that extra bit of information. And if I did not tell people what their concentrations were. And in fact, they had different concentrations because we saw they had different equivalence volumes. Now, you could back out what the equivalence volumes are, and then you could determine the concentrations. But again, at that point, you are not just looking at that initial pH value. You are now also taking into account the equivalence volume, meaning that you have done the entire titration and you have all the titration data. So at that point, yeah, you could figure out the Ka value based upon using the half equivalence volume, or sorry, using the equivalence volume here. So you can say that the concentration of the HCl should be equal to the concentration of your base times the volume of base that you added, which would be your equivalence volume, divided by the volume of acid that you started with. Yeah, then you can get the molar concentration of, I'm sorry, that should be HF or some weak acid. Then you could figure out the concentration of your weak acid, and then you could figure out Ka. But again, at that point, you've already done the full titration anyway, so why not just use the approximation and say pH is equal to pKa at the half equivalence point. And then another question here also doesn't, so could you please clarify, the equivalence volume doesn't depend on pH, correct? Yes. Generally speaking, the equivalence volume only depends on the concentration of your analyte, of the acid that you're analyzing, how much acid you need to neutralize. It depends on the concentration of your titrant, the base that you're using to neutralize your acid, and it depends upon the volume of acid that you were using originally. Again, the equivalence volume is the point. It's called equivalence because it's when you have an equivalent amount of acid and base mixed together. So we define the equivalence volume when moles of acid is equal to moles of base if you're doing an acid-base neutralization reaction, and they're both monoprotic. So that's how we define the equivalence, and that's not necessarily dependent on pH. It could be related to pH if you were dealing with a strong acid neutralization, and then there's a direct correspondence between the concentration, the moles of your acid, and the actual pH. But if you're dealing with a weak acid, it's not a linear correspondence. It actually goes as the square root here because you have to do an icebox calculation. Okay, a couple of other just side notes here. So those are all the feedback questions. A couple of comments people had. Could you please only use white chalk? I was sitting in the front row and I couldn't see. I will try to use more visible color, visible chalk. I recognize maybe red was not a good choice on a green chalkboard. So I will try to stick to lightly colored chalks like orange, yellow, white, because I like having a few colored chalks, a few different colored chalks for like emphasis, or if I want to annotate a graph or something. But I will try to be more careful with my color choices. Secondly, what do I need to know for the quiz on Wednesday? So the quiz on Wednesday is going to discuss acid-base chemistry. So I expect everybody already knows things like the Arrhenius definition of acids and bases, how to calculate the pH of a strong acid, how to calculate the pH of a strong base. So there might be one question about that, but so you should. it is more, I think, going to focus on acid-base equilibria. So either calculating the pHs of weak acids and weak bases, thinking about buffer solutions and having multiple substances in solution, analyzing a solution and deciding what are the major species present, so on and so forth. So yeah, make sure you know how to calculate the pHs of weak acids and bases. Make sure you know how to predict the acidity of a salt based upon whether the ions in that salt are basic or neutral, whether they're the conjugate bases or acids of strong, or rather of weak acids and bases. Please make sure you know the classifications of acids, like Arrhenius versus Bronsted-Lowry. That will be the focus of the quiz. Okay, so that is all the feedback for today. If people have any other questions, please feel free to bring them to me either via email or during office hours, and I will see everybody on Wednesday.